Hello and welcome to our fourth lecture. Today we're going to learn about subspaces. So let me tell you first what are subspaces. So pretty much what you should think of is that a subspace of a vector space is just a subset in terms of elements. And then the second most important part is that it's going to be a vector space over R in its own right. And it's going to be a vector space with the same operations. So this is where part 2 comes in. So what you have is that if you restrict the operations plus here to the Cartesian product W and W, then, well, what should this land? And this should land in W. So this pretty much just says that if you have W1 and W2 in W, well, then W1 plus W2 is in W. So exactly what I've written down here. And then the second part here will say that if you have lambda in R and W in W, well, then you also have that lambda times W is in W. Okay. So overall, let me just read it out loud. If we start with a vector space with operations plus and scalar multiplication is given, and we take a subset of that space, then this is a subspace if the operation restrict to the subset, and, well, W will form a vector space in its own right. So let us look at a couple of examples here. So first, let us take a set which is a subset of R2. So this, for example, where restrict to all tuples in R2, which are of the form something comma 0, is a subspace of R2. Secondly, and this is something that is true for every vector space, so suppose we have V, a vector space over R. Then if we take the set 0V, which is a subset of V, this is always a subspace of V. Well, and also the full space is always a subspace, and V is a subspace. So note here, right, the subset thing, it includes being equal to the whole thing. And let me maybe give you a non-example. Let's look at the set A, B, C, such that A squared plus B is equal to 0. Well, this is not a subspace. Well, how can I see that? What I want to see is here that that, for example, scalar multiplication or addition will not hold. So let us look at the following element. So let's say we have here 1 minus 1, 0. Well, then here we have that 1 squared plus minus 1 is equal to 0. Thus, if we call this set S here, we have that 1 minus 1, 0 is an S. Well, but let's look at this here. Let's say we do minus 1 times 1 minus 1, 0. This is equal to minus 1, 1, 0. And in this case, now we have that minus 1 squared plus 1 is equal to 2 is different from 0. So this minus 1 times 0, 1, 0 is not an element of S. thus, S is not closed under scalar multiplication, and hence it's not a subspace. In this case, of what? Of R3. Okay, so these are examples, but then also in part 1 and 2, we would need to prove that something is a subspace. And so it seems rather lengthy. Yeah? If you look back at this definition, we have to, well, check that it's a subspace. We have to check that it restricts. And then what becomes really lengthy is this last part over here. Yeah? This last part is saying it's a vector space in its own right. And you will already notice in this week's homework that checking that something is a vector space is very elaborate, right? Because you have to check that all the 8 axioms hold. And this is very time consuming. So it would be nice to have a way of checking that something is a subspace in a faster way. So let us look at this following theorem. Yeah, and we often call this here the subspace test. And this is a very important theorem, and pretty much from now on, after we've proven this, you will never ever want to go back to the definition of a subspace to show that something is a subspace, but you want to use this theorem. Okay, so what does it say? Well, taking a vector space V with given operations and a 0 element 0, and now we take here a subspace set W of V, and we want to characterize when is this subset a subspace. Okay, so for a subspace, let's go back to the definition. We have to have it's a subset, we have to have the operation restrict, and it's a vector space in its own right. Okay. So now in this case here, let me add over there. In this case here, subset is already given. Okay, and now we say, well, it's a subspace if and only if, this is something important, I will say more about it later. If and only if, well, this 3 condition holds. The first one is that the 0 is an element of the set. The second one basically codes that it's closed under addition, and the last one codes that it's a closed under scalar multiplication. And so now, as I said, this is an if and only if statement, and we're coming to a new proof strategy. How does one prove if and only if statements? So an if and only if statement tells you that there's both directions, yeah? So this will tell you if W is a subspace, then well implies that this holds, so this direction, but it will also tell you that the other direction follows, yeah? That if we have these 3 properties over here, then W is a subspace. So that has to be reflected in our proof. So let's look at this. We want to show an if and only if statement. And so we have these 2 directions, yeah? And this is how I usually denote it. I will let you know which direction I prove. So we want to show that some statement A holds, and so statement A in our case would be W is a subspace. If and only if another statement B holds, and here in our case that would be these 3 conditions. So the way we go is, well, first direction, we want to prove B holds whenever A holds. So we assume A holds. We use mathematical reasoning using A to obtain B, and then we conclude B holds. Okay? And then the second part goes very similar. Now we go the other direction. We start with assuming that B holds, then using the statement B and consequences, we want to obtain A, and then we include A holds. So pretty much the main part you want to keep in mind is always you have to do both directions. You have to do the first statement implies the second, and then the second implies the first. And so now we're going to put this into action. So proof of theorem 3.5. So as I said, this is the way I denote it. I tell you this arrow, and this arrow now, what does it mean? Well, suppose W is a subspace of V. And now we want to show that 1, 2, 3 holds. Okay. Let's go back. We want to show the 0 is inside and it's closed under addition and scalar multiplication. So I'm going to start with 2, 3 actually here, because this is basically given by the definition of being a subspace. So by definition of a subspace, the operations plus and multiplication, scalar multiplication, restrict to these two things. And this implies immediately 2 and 3. So it is left to show that 1 holds. Okay, and so note here, and this is something important again here, that the 0 is the 0 in V, yeah? And so for the moment, when you take a subspace, you don't know that the 0 in the subspace is the same 0 as in the big vector space. You do know that the subspace has a 0, because you do assume by definition here, let's go back, yeah, that it's a vector space in its own right. And every vector space has a 0. But as pointed out before, the 0 could differ, yeah? As W is a subspace, is a vector space, let's write it like this, is a vector space in its own right, there is a neutral element in 0. Okay, which I denote by 0W. And now we want to show that 0W is actually the same as 0V. So we need to show this is equal to this, where 0V is in V is the 0 in V. Okay, and this goes very much similar to show that the 0 is unique in a vector space. So that is start by 0V plus 0W. This by axiom 1 is 0W plus 0V. This now by axiom 3. And I want to be careful here. Where am I doing it? I'm going to use axiom 3 in V. Yeah, because we have 2 different vector spaces around. So we kind of have to tell you where you do this. Yeah, because axiom 3 in V corresponds to the 0 in V, and then axiom 3 in W corresponds to the 0 in W. Okay, so this becomes this. And then now we use axiom 3 in W, and we can add this old W. And now by cancellation law, we obtain that 0V is equal to 0W as required. And then we're done with this direction. Yeah. So let's go back to the statement. We've shown 2 and 3 is immediately from being a subspace, and then number 1 we just showed because we showed that the 0 in W is equal to the 0. Okay. So let's now do the other direction. So we suppose now that this 3 statement hold for some W. So suppose that for W subset in V statement 1, 2, and 3 hold. Okay. And now we want to show that it's a subspace, and so we have to go back to the definition. You might want to put it up on your screen so you can double check. So we want to show what? We have to show it's a subset. That's the first part. But this we have because we assume that W is a subset. Okay, so this is good. Then the second part was to show that addition and multiplication restrict, but this is part 2 and 3. Yeah. So assumptions 2 and 3 ensure that the operations in V restrict to operations in W. And so now it is left to show that W is a subspace in its own right. And so we have to go through the list of axioms. And some of them is just very much, it's just really due to the fact that you inherit them from the big vector space. And I'm going to write it down, but then I'm going to say a little bit more to it. So axiom 1, 2, 5, 6, 7, and 8 all hold because they hold in V. Okay, so I'm going to scroll, but I'm going to get back to it. Okay. So what do I mean by that? So this is, again, a good time for you to pull out those list of axioms and look what is written there. If you look at axiom 1, 2, and 5 through 8, they are a little different type than the ones than 2, 3, and 4. Yeah. So 1, 2, 5, 6, 7, 8 are statements that say for all elements something happens. Okay. And so now, since you restrict to a subset, yeah, for all those it will still be true because it was true for all elements in V. Hence, it has to be true for all elements in W, since W is a subset. So what is different for axiom 3 and 4? Well, 3 and 4 talk about they exist something. So if I restrict to a subset, yeah, I know it exists in this bigger set, but it doesn't ensure now to exist in the smaller set. So we still have to show that these hold. Okay. But now, so let's start with axiom 3. By assumption, we have that 0 is part of W. And as I said before, when we assume it's a subspace, we cannot assume that this unique neutral element is necessarily the same. But in this case, we have 0 in W, and we know 0 acts as a neutral element for elements in V, and V again is bigger, so will act as a neutral element for all elements in W. So this is enough now. And now it's left to show that axiom 4 holds. So for axiom 4, suppose W is an element in W. So now we want to show that the unique additive inverse is also in W. And first what we're going to do is we're going to go to the bigger space, and there we know we have additive inverse. So because V is a vector space, we have the multiplicative inverse minus V is an element in V. So it's left to show that this is also in W. And now we go back to the consequences of the axioms of vector spaces. So by theorem 3.36, so this is the ones that are immediate consequences from the, not immediate, but consequences from the axioms. We know that what? We know that minus W, oh, sorry, this should be minus W here. Yeah. Minus W is equal to, well, minus 1 times W. But now this is an element of W by assumption 3. Yeah, assumption 3 told you when you have an element here in W and you multiply it by something in R, this will remain in W. And so now this marks the end of the proof. And so from now on, you can always just go back here, and when you want to show something as a subspace, the only thing you have to show is the 0 is inside, it's closed under addition, and it's closed under scalar multiplication. And another thing that is a consequence here is that the 0 in V is also the 0 in W. So you can also assume that now. Every time you take a subspace, you can take for granted that the 0 that was at the bigger space is also the 0 in the smaller space. And we're almost at the end now. There is another theorem 3.6 in the lecture notes. This will be done in the TA session, so it's more equivalent conditions of being a subspace. And so the only thing I want to do now is look at a couple of examples. Number 1, x1, x2, x3, x4 in R to the 4, such that 8x1 plus 18x2 plus 88x3 is equal to 0, and 7x2 plus 14x3. I don't know what I wrote here. Okay, this is a subspace of R4. With the usual addition and scalar multiplication. And what you should keep in mind here is that such sets are usually subspaces whenever the conditions here, these two, are homogeneous linear equations. Yeah. So what you want is that there's a 0 here, and then up here you only have linear terms. Okay, great. Then the set of even functions is a subspace. So remember what they are if you, or just, I'll tell you what they are if you haven't seen them. For all t in R, f of minus t is equal to f of t. And also the set of odd functions. So this is the a subspace of the set of all functions, or R. we have that PNR is a subspace of PMR if n is less or equal to m. Yeah, so the polynomials of degree at most m is a subspace of the polynomials of degree at most m. If m is larger, and a subspace of all polynomials. And then there's a sixth part of it in the lecture notes, and I will go over that in the live lecture and tell you more about it. So this marks the end of today's lecture. I wanted to let you know that in this case here, we haven't proven any of these are subspaces. So I'll just told you that. So as an exercise, I leave that to you at home, is to show that all the above are subspaces. Okay, so hope to see you all on Wednesday. Bye-bye.